Okay, there. Now we can start. So we talked about how equilibrium can be determined in the context of molar concentration or for gases with pressure. And so instead of putting the molar concentration in there, you just put the pressure in your equilibrium expression. And then we said that if we take our ideal gas law, PV equals nRT, and we get P by itself, and then we crunch it in with the equilibrium expression, and we do some derivations, we get that the equilibrium pressure constant is equal to the equilibrium molar concentration constant times gas law times temperature raised to the power of the change in the molar concentrations, okay, or the coefficients. And I said that I'm not concerned about you guys going from PV equals nRT and K and the equilibrium expression and deriving this formula, but just know how to use this formula because we have problems where we'll have to solve for Kp, or we'll have to solve for Kc, or maybe the temperature or the change in moles, that kind of thing, depending on what we're given. And the change in moles, so that delta N, is always going to be the moles of product minus the moles of reactant. Okay, so whatever the coefficient on the product side is, minus the coefficient on the reactant side. And then I think I left you with this problem, but I don't think we actually solved it. So let's go for it. Let's see what we can do. You want to? It says nitrogen monoxide is oxidized into nitrogen dioxide. And it gives us a Kp, it gives us a temperature, and it wants us to find the Kc. So what do you guys think would be the setup for this? Kp equals Kc times RT to the power of delta N, right? Where's my eraser? Did I bring that? Maybe I forgot to bring my eraser down. Okay, I'll be right back. You guys try and set that up while I get the eraser. Okay. All right, so our Kp is 2.2 times 10 to the 12. And they want us to find Kc. R is 0.8206 liters atmospheres over mole K times, it's 25, so 298.15 K to delta N. What do we get for delta N, guys? Anybody? What do you think delta N is?
Is it 1?
Close. So let me go back. Sorry. Let's go back to that slide. We got on the reactant side, we got a 2. And then essentially a 1. So 2 plus 1 is 3. And then on the product side, we have 2. And remember, it's products minus reactants. So 2 minus 3, it's a -1. So this is all going to be to the -1.
And you knew which direction to go based on how the problem was set up, like in the word problem? No.
It's always products minus reactants.
I guess I'm just still confused by the arrows going both ways about knowing which is which.
Okay. When you see a reaction, always assume that the reactants are on the left side and the products are on the right side. If there's more than one arrow, that just means it can go back and forth. So remember we talked about the jugglers on Tuesday, and they're sending the pins back and forth, but you can always consider the juggler on the left side to represent the reactants, and the juggler on the right side to represent the products. The products will never be on the left side, but it can go back. The arrows going back and forth show just as saying that something forms a product, and then at some point that product goes back into the things that made it, goes back into the reactants. Okay, so to get KC by itself, we just divide each side by 0.08206 times 298.15 to the -1, right? So 2.2 times 10 to the 12 divided by 0.08206 liters, atmospheres, moles, K, times 298.15 K to the -1 equals KC. And what do you guys get if you do that? Buddy?
Uh, 5.4.
Just 5.4?
Well, I only kept 2 sig figs because of the 2.2. But
Okay.
I got 5.3825.
No other zeros after that, or
Oh,
before?
times 10 to the
Okay.
13th power.
Okay, all right,
That's,
there we go.
yeah.
Okay. Anybody else get something different, or is that?
I got the same.
Okay, there's a consensus. Great. 5.4 times 10 to the 13. So really pretty basic at this point, right? Just you're missing one variable, you solve for that variable. It's just straightforward algebra for that kind of a thing. When talking about equilibrium, there's this concept called Le Chatelier's principle. And what that says is if a system is at equilibrium and you disturb that system by one of the 3 things we talked about on Tuesday, the things that change equilibrium, temperature, pressure, or concentration, and now it's no longer at equilibrium, there will be a shift in the system to counteract that, that disturbance and bring it back to equilibrium. Okay? So again, if you have a system at equilibrium and you disrupt that equilibrium, it will shift either the products or the reactants to reach equilibrium again. That's all it is for now, okay? So temperature, pressure, concentration, those are the things that can do this, right? If we have a reaction and we have equal amounts of aqueous cobalt and chlorine, and we change the temperature, then we can shift it one way or another. By changing the temperature, if it was the equilibrium in this first panel here, right? Let's say this is at equilibrium. Not at equilibrium because there are equal numbers of cobalt and cobalt chloride, tetrachloride. But just because the rates are going back and forth at the same rate, we change the heat, we can drive it one way or another. And if these molecules have a certain color, right, we can drive it toward more cobalt tetrachloride. If we say remove the heat, or if we add the heat, adding heat, we get cobalt tetrachloride. If we remove the heat, then we get a color change, but that's because we've shifted the equilibrium toward the product, the reactant side, aqueous cobalt, okay? So playing with temperature, we can treat the reaction and therefore the energy associated with that reaction as a product or a reactant. Now, if we look at volume, let me get rid of that. Same kind of thing, okay? We have the volume of a reaction, we change it. The system that is being changed based on Le Chatelier's principle is going to try and counteract that change by producing fewer gas molecules, for instance, to keep the pressure the same, okay? Now, if there are equal numbers of gas molecules on both sides of that reaction, then changing the volume isn't going to change the equilibrium, right? It's just going to compress it, and it's going to put them in more close proximity to each other. But if we have different numbers of reactants and products, and we change the volume, it will change the equilibrium to where there'll be a different rate of either the products or the reactants being made. Okay. So concentration, temperature, volume disturb equilibrium, leading to a shift on one side of the arrow or the other to then come back to equilibrium. Okay. Let's say we have, this is our Haber process again, right? Making ammonia from hydrogen and nitrogen gas. If we added more hydrogen gas to a system at equilibrium, the reaction proceeds toward the product, okay? I'm just telling you that. So you have H2 plus N2 yields NH3. You add more H2. Now there's an imbalance. It'll shift toward the product. A little review from Tuesday. Does that make the Q larger or smaller than K? You guys remember? if we're going toward products, what's the relationship of Q and K?
K is larger than Q.
Exactly. If the shift predominates toward product, K therefore must be larger than Q. If the shift proceeds toward reactants, Q is larger than K. And so remember what I said on Tuesday, in industry, when you're trying to produce something, then if you don't get a full shift toward product, there are certain things you can do to perpetuate the reactions, to perturb equilibrium, essentially, so that it continues to shift toward the desired product. And so for making nitrogen or making ammonia, we can have a system where we pump in, here we're pumping in the nitrogen and hydrogen. It travels down here, and then it gets heated up. And in the process of being heated, it forms our product, our ammonia. That ammonia then circulates up here and is pumped through this tube and then is condensed. Okay, so we cool it off and it'll condense the ammonia, but not the nitrogen and the hydrogen. And so it essentially, that ammonia drops out of this apparatus. And so anything that didn't form ammonia, right? The leftover nitrogen and hydrogen does not condense, and it gets pumped back into the system. And guess what? Since you've removed the ammonia by condensation, you've disrupted equilibrium, and now that leftover nitrogen and hydrogen are going to go be driven toward the products, and you're going to make more ammonia. So by removing something from the system, it will drive the reaction one way or another, depending on what you're removing. Okay. Now, let's say we want to relate free energy and equilibrium. All right, there was an ICA problem or two dealing with this. If we have standard or non-standard conditions, it doesn't matter. We can relate free energy and equilibrium as the following. We can say that delta G is equal to that standard free energy value, delta G plus RT natural log Q. Now, if it's at equilibrium, remember, Q and T are equal. And at equilibrium, delta G is 0. Remember the tables that I showed you of looking at spontaneous, non-spontaneous, reversible, equilibrium, that kind of thing. Delta free energy does not change when the system is at equilibrium. So knowing those things, when the system is under equilibrium, we can put in K for Q, right? So we can change the equation by saying, well, if K and Q are equal, then I'm just going to put K in here instead of Q. And if delta G is 0, right here, it's at equilibrium. So this delta G is at 0. We can say that 0 equals standard free energy plus RT natural log K. Okay. And so if you want to find K, you can then rearrange that equation to get this. So what does a problem like that look like? Oh, hold on. Before we jump into the problem, it's important to know that the gas law isn't going to be that 0.0206 because the units are different now. We use this gas law, this one, when we were using the context of pressure, right? What are the units? Liters per atmosphere. Delta G is not liters liters times atmosphere, right? Anybody remember what delta G is? What the units are for that? Anybody? Okay, I'll give you a hint. It's very similar. Oh, maybe someone put a chat in there. It's very
Kilojoules per Kelvin.
joules per mole. Yeah. Okay. Now, we need to use a gas law that's not going to introduce additional units like atmospheres. So in this case, R is going to be 8.3145 joules per mole Kelvin. Okay. So with that in mind, let's do this problem. Use the tabulated free energies of conformation. So get to that good old Appendix G in your textbook and use that to calculate the equilibrium constant for the reaction at 298 K. So you look up those standard free energies for nitrogen dioxide and dinitrogen tetroxide, and you do products minus reactants to give you your delta G, and then you plug in the R and the K, and then you have everything you need to solve, I'm sorry, R and K meaning, K as in Kelvin, R and temperature, and then you have everything you need to solve for K. Okay. So let's try that. I want you guys try to set it up, try to get that delta G, because that's going back to a review of stuff we did. What was that, last week? We'll see what you get. I'll look it up too on my end. Where's my textbook? Here. Okay. All right, so somebody's already found them. Go ahead and shout it out. Save some time. Two guys. Oh, no.
We're looking at the delta G, right?
Correct.
Okay, so for N2O4, it is 99.8, and for NO2, it is 51.30, and they're both in their gas state.
Yep. Great. And then we multiply that one by 2, right? Because of the coefficient. Great. So it's going to be delta G is equal to 51.30 times 2 times, or sorry, minus 99.8. Okay, what do you guys get for that? $102.6 minus 99.8.
2.8.
2.8. And then what are our units? They're kilojoules per mole. Okay. Now, that's our delta G. So what do? We say, we go back to our equation here. Oops. We can say that 2.8 kilojoules per mole is equal to a negative 3.1 or 8.3145 joules per mole, or yeah, joules per mole, okay, times 298, I think they gave us, times the natural log of K.
So we still need to get kilojoules to joules, right?
Yes, exactly. We want to make sure that our joules, or that our units, are the same. And so another way to rewrite this, because we're wanting to solve for K, we can say that the natural log of K is equal to a negative delta G over RT, right? We could say a negative 2.8 times what? 10 to the third joules per mole over 8.3145 joules per mole K times 298. What do we get for that? Anybody get something yet?
Negative 1.13.
1.13 equals the natural log of K. Great. Now, that's not our answer because that's equal to the natural log of K. We want K by itself. So the way that we can do that is what you can say, if the natural log, you can say the natural log of K is equal to E to the negative 1.13. if natural log of K equals negative 1.13, then essentially K is going to take this value and raise e to the power of that. So what that would look like is you would take on your calculator, for mine, it's e to the x. So you type in negative 1.13, and then you hit that e to the x button, and what do you get?
0.323.
Okay. And that is our K. Okay, guys? That feel all right? All right. What I'm going to do is I'm going to skip over this because I want to get in enough time to do some other things. But remember, practice makes permanent. So I recommend that you guys try these. And maybe we can go over them during office hours next week or sometime if you'd like, or you guys can get in groups. But you essentially do the same thing for these problems. You look up the standard change in free energy values for H, F, and HF. You subtract products. You take products, subtract reactants, gives you your delta G, and you set it up from there. Okay. Standard temperature, so 298. You use the gas law and see what you get. Okay. So some practice for you guys if you want to do that. It's gonna be the same way as what we did before. If this doesn't quite gel, maybe come back to the recording and watch the recording again and see how we went over this. Okay. But what I want to do now is I want to get back into equilibrium expressions and things like that. Okay. So we had a little bit of a foreshadow of this on the ICA. Now I'm going to spend probably the rest of the lecture. If there's some time, we can go back and do some of these problems. But for now, let's say we have a reaction, carbon monoxide plus hydrogen forms methanol. And we know that the reaction mixture is at 780 degrees and contains a couple concentrations. They give us the concentration of carbon monoxide at 0.5 molar and hydrogen gas at 1 molar. And then it says at equilibrium, the concentration of carbon monoxide is 0.15. What is the equilibrium constant? Does anybody know what we would do to set this problem up? All right, I'm going to give you a hint. Anybody get it yet? No, still?
An ice table.
Ice table, right? Ice, ice, baby, vanilla ice. That you guys may be too young for vanilla ice, but
I was actually thinking of
Under
under pressure.
ha, yes. Well, so that's a very touchy subject. So Queen and David Bowie came out with the song Under Pressure, which would also be a good song to play when we're talking about pressure. And clearly Vanilla Ice sampled or ripped off that baseline. But of course, he never to this day will admit that he did, because he says they're different. His is dun 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 dun. And he says that under pressures, dun 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 dun. So splitting hairs, I think. But yes, not to be confused. They're both very different songs outside of that little bass lick. But anyway, ice tables. So ice baby, guys, that's what we're going to do. Remember, with ice tables, we start by just writing out the reaction, which is carbon monoxide plus 2 hydrogen yields methanol, H3OH. Okay? And then we write ICE. And I'll once I get this data in, I'll stop sharing my screen so you can see this a little bit better. And then initially, the reaction mixture at 780 degrees Celsius initially contains blah, blah, blah. Initially, ice, initial. So we just put in the information that we have. So 0.500 for carbon monoxide and 1.00 for hydrogen. What is our methanol?
0.
0. Great, thank you. What else does it give us? At equilibrium. E. Initial change equilibrium, ice. It is 0.15 for carbon monoxide. So 0.15. What is the equilibrium constant? Okay. So now we fill in the rest. What can we do? This is all we need to solve the problem, because we know that we start off with 0.5 and we end up with 0.15. So the change must be the difference of those two, right? And so what is that? Is it 0.35? I think, yeah. But it's a negative 3.5, because 0.5 minus 3.5 is 0.15, right? So that means on the reaction side, the reactant side, it's going to be negative. This is essentially X, all right? So later on, we won't know what the change is, and we'll have to figure out the change. But for now, we're going to say that that is the change. So it must be negative 0.35 here too. But because we have to take stoichiometry into consideration, what do? We multiply it by 2, right? Because of the coefficient. And then, so that difference must be this product's gain. So it loses 0.35 in concentration and what? 0.7, and it gains 0.35 here. And so what is our equilibrium? One minus 0.7 is going to be 0.3. And 3.5. Okay. What's the problem asking for? It's asking for K, I think. Let me double check. Yeah. What is the value of the equilibrium constant? How would we solve for K now that we have this? What will we do? Hint. Equilibrium expression. Right? K equals what over what? Products over reactants. So the concentration of 3.5 over the concentration of 0.15 times the concentration of 0.30 squared, right? Because we take it to the power of the coefficient. And if you just crunch that, what do you get? Oops.
$2.1.
What'd you get?
2.1.
0.1. Okay. Anybody get something different? I'm getting 25.9.
Yeah, I think I put it in the calculator wrong.
Okay. Anybody else get 29 or 25.9?
I got 25.9.
Okay.
On your equation, it says 3.5 up top, and it should say 0.35.
Oh, that's why. Sorry. Thank you for that correction.
Wait. Oh yeah, 0.5. Okay. I see.
Oh, and I got it right here too. Yeah. So I was thinking 0.35, but I put that. Thank you, my autocorrect. That's why I got to do these lectures live. Okay. So let's do another one. If you guys haven't gotten all this written down yet, come back to the video and check it out. There we go. Okay. So that's that one. What happens when we have a different reaction? And what does it give us here? This time, it gives us the initial concentration of methane, and it gives us the equilibrium concentration of ethane. So I'm going to let you guys, I want you guys to set this one up. Try to set it up. Write out the reaction. Write ice down the side, and then fill in what you have, and then what you don't have, you know, we'll figure out what to put in the place, right? initial point 115 equilibrium ethane is 3.5. All right, hopefully you guys got to hear so far. I just got my initial concentration and the equilibrium concentration that I'm given. If this is initially 0.115, what is ethane and hydrogen gas going to be?
0.
0. Okay. So how do we know what this must be? 0 and what kind of change gives me 0.035?
Minus X.
Close.
Plus X.
So just think of it in terms of what the difference is here, right? So if it was minus 0.035, 0 minus 0.035 is going to be a negative 0.035. But in this case, because we're going from 0 to something greater than 0, it's a gain. So it's a increase. So the positive change, okay? So that's going to be, this must be plus 0.035. And then this must be 0.035 times 3. And what is our change on this side?
Minus 2 times 0.035.
Yeah, so minus 0.035 times, let's keep it, times 2. Okay, so what is this? A negative 0.070, I think. And what's 0.035 times 3? .09 plus.
Wait, for the first one, I got 0.045 positive.
I got the same.
For this one?
Yeah.
Yes.
Okay.
But it's positive, not negative.
Oh, you know what, guys? Yeah, I was just writing down, I messed up. I was just writing down 0.035 times 2. And that's a negative 0.07. But I forgot to subtract it from this. Okay, so what did you get? A positive?
It's 0.045.
0.045 for the final answer. Thank you, guys. Okay. And then this, yeah, I forgot that initial concentration. So now this one is what?
.105.
0.105. Okay. And so K is 0.035 times 0.105 to the third over 0.045 to the second. What do we get there?
0.02.
Okay. Any questions on that? This is as easy as it gets for the ice tables. Okay. We're going to take a break. And when we get back, we're going to have to solve when we can't extrapolate what the change is. So we have to put X in there. We have to determine which direction the reaction's going. And then maybe we'll have problems where they give us K, and this time we got to solve for X, that kind of a thing. Or we get X and we have to find the equilibrium concentrations, so it's going to build upon this. Take a 10-minute break, rest your head, take some deep breaths, get some drinks, a snack. I'm going to play Ice Ice Baby for those of you who want to stick around, get you guys kind of in the groove. And then we'll come back at 2:10 and carry on with some more ice tables, okay? See you in a bit.
Yo, VIP. Let's kick it. Ice, ice, baby. Ice, ice, baby. All right, stop. Collaborate and listen. Ice is back with the brand new invention. Something grabs a hold of me tightly. Flow like a harpoon daily and nightly. Will it ever stop? Yo, I don't know. Turn off the lights, and I'll glow. To the extreme, I rock a mic like a vandal. Light up a stage and wax a chump like a candle. Dance, rush the speaker that booms. I'm killing your brain like a poisonous mushroom. Deadly. When I play a dope melody, anything less than the best is a felony. Love it or leave it. You better gain weight. You better hit the bullseye. The kid don't play. And if there was a problem, yo, I'll solve it. Check out the hook while my DJ revolves it. Ice, ice, baby. Vanilla. Ice, ice, baby. Vanilla. Ice, ice, baby. Vanilla. Ice, ice, baby. Now that the party is jumping, with the bass kicked in and the Vegas all pumping, quick to the point, no faking. Cooking MCs like a pound of bacon, burning them. You're not quick and nimble. I go crazy when I hear a cymbal and a hi-hat with a souped up tempo. I'm on a roll, it's time to go solo. Rollin', hit my 5.0 with the rag top down so my hair can blow. The girl is on standby, waiting just to say hi. Did you stop? No, I just drove by, kept on. Pursuing to the next stop. I bust a left and I'm heading to the next stop. The block was dead, yo, so I continued to A1A, Beachfront Avenue. Girls were hot, women less than bikinis. Rock men lovers, driving Lamborghinis. Jealous, cause I'm out getting mine. Jay with the gauge and vanilla with the 9. Ready for the jumps on the wall. The jumps acting ill cause it's full of 8-ball. Gunshots ranged out like a bell. I grabbed my 9, all I heard was shells falling on the concrete real fast. Jumped in my car, slammed on the gas. Bumper to bumper, the avenue's packed. I'm trying to get away before the jack does jack. Police on the scene, you know what I mean? They passed me up, confronted all the dope fiends. If there was a problem, yo, I'll solve it. Check out the hook while my DJ revolves it. Ice, ice, baby. Vanilla. Ice, ice, baby. Vanilla. Ice, ice, baby. Vanilla. Ice, ice, baby. Take heed, cause I'm a lyrical poet. Miami's on the scene, just in case you didn't know it. My town, that created all the bass sound. Enough to shake and kick holes in the ground. My style's like a chemical spill. These are rhymes you can vision and feel. Conducted and formed is a hell of a concept. We make it hype, and you wanna step with this. Shape plays on the fade, slice like a ninja, cut like a razor blade so fast. Other DJs say, damn, rhyme was a drug, I'd sell it by the gram. Keep my composure when it's time to get loose. Magnetized by the mic when I kick my juice. If there was a problem, yo, I'll solve it. Check out the hook while my DJ revolves it. Ice, ice, baby. Vanilla. Ice, ice, baby. Vanilla. Ice, ice, baby. Vanilla. Ice, ice, baby. Vanilla ice. Yo, man, let's get NRT. Let's kick it. Ice, ice, baby. Ice, ice, baby. All right, stop. Collaborate and listen. Ice is back with the brand new invention. Something grabs a hold of me tightly. Flow like a harpoon daily and nightly. Will it ever stop? Yo, I don't know. Turn off the lights, and I'll glow. To the extreme, I rock a mic like a vandal. Light up a stage and wax a chump like a candle. Dance, rush the speaker that booms. I'm killing your brain like a poisonous mushroom. Deadly. When I play a dope melody, anything less than the best is a felony. Love it or leave it. You better gain weight. You better hit the bullseye. The kid don't play. And if there was a problem, yo, I'll solve it. Check out the hook while my DJ revolves it. Ice, ice, baby. Vanilla. Ice, ice, baby. Vanilla. Ice, ice, baby. Vanilla. Ice, ice, baby. Now that the party is jumping, with the bass kicked in and the Vegas are pumping. Quick to the point, no faking. Cooking MCs like a pound of bacon. Burning them, you're not quick and nimble. I go crazy when I hear a cymbal and a hi-hat with a souped up tempo. I'm on a roll, it's time to go solo. Rolling, hit my 5.0 with the rag top down so my hair can blow. The girlie's on standby, waiting just to say hi. Did you stop? No, I just drove by, kept on. Bust on to the next stop. I bust a left and I'm heading to the next stop. The block was dead, yo, so I continue to A1A Beachfront Avenue. Girls were hot, women less than bikinis. Rock men lovers, driving Lamborghinis. Jealous, cause I'm out getting mine. Shade with the gauge and vanilla with the 9. Ready for the jumps on the wall. The chumps acting ill cause it's full of 8-ball. Gunshots ranged out like a bell. I grabbed my 9, all I heard was shells falling on the concrete real fast. Jumped in my car, slammed on the gas. Bumper to bumper, the avenue's packed. I'm trying to get away before the jack does jack. Police on the scene, you know what I mean? They passed me up, confronted all the dope fiends. If there was a problem, yo, I'll solve it. Check out the hook while my DJ revolves it. Ice, ice, baby. Vanilla. Ice, ice, baby. Vanilla. Ice, ice, baby. Vanilla. Ice, ice, baby. Take heed, cause I'm a lyrical poet. Miami's on the scene, just in case you didn't know it. My town, that created all the bass sound. Enough to shake and kick holes in the ground. My style's like a chemical spill. These are rhymes you can vision and feel. Conducted and formed is a hell of a concept. We make it hype, and you wanna step with this. Shape plays on a fade, slice like a ninja, cut like a razor blade so fast. Other DJs say, damn, rhyme was a drug, I'd sell it by the gram. Keep my composure when it's time to get loose. Magnetized by the mic when I kick my juice. If there was a problem, yo, I'll solve it. Check out the hook while my DJ revolves it. Ice, ice, baby. Vanilla. Ice, ice, baby. Vanilla. Ice, ice, baby. Vanilla. Ice, ice, baby. Vanilla ice. Yo, man, let's get out of here. Word to your mother. Ice, ice, baby. Go. Ice, ice, baby. Go. Go. Ice, ice, baby. Go. Ice, ice, baby. Go. 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 Ice, ice, baby. Go. Ice, ice, baby. Ice, ice, baby. Go. Ice, ice, baby. Go. Ice, ice, baby. Go. Ice.
After listening to the entire song, I have concluded they totally ripped off Queen. They totally did. Like even the piano chords at the end is the same. Like the bass line and the piano chords are the same.
You'll have to take that up with Vanilla Ice, Hannah. Yeah, well, guys, I hope that you were also dancing along like I was during the break to get the blood flowing a little bit. I also hope that your dance moves are probably better than mine because mine are pretty terrible. That's why I turned my camera off. But, you know, never should we take ourselves so seriously that we can't have fun. So anyway, welcome back. Hopefully you had a nice break. And now we're going to continue with the ice baby, doing some ice tables to figure out equilibrium concentrations. Okay. So with that, let's get back into it. There it is. Okay. So now it's going to be a little bit trickier. They give us a reaction. They give us a Kc, an equilibrium constant, and they give us a few initial concentrations. They don't give us any change or equilibrium concentrations. So they want us to find the equilibrium concentrations to do that. Okay, so how would we set this up? Well, again, as with always, we write out the reaction. And then we write ice. And then we write what we're given. So at 2000 degrees, nitrogen is 0.2. And oxygen is also 0.2. So then our nitric oxide is 0. Okay. First thing we need to do is figure out which direction this thing is going. How can we do that? Any guesses? What else am I forgetting? They gave us, okay. Where am I going to write that? K is 0.10. Okay.
Wait, isn't it 2NO on the product side?
Yes, thank you. Perfect. Great. All right. That's important, right? Don't want to miss that too, because that'll change the answers entirely. How can we find which direction this is going based on what we're given? Well, we have K. How do we know which way it's going? We relate K to what? That other letter.
Q.
Q. Okay, thank you. Thank you, Rachel, for typing that in. So Q, how do we know what Q is, right? Q is the same ratio, just not necessarily at equilibrium. Well, we have concentrations, right? We have 0 squared over 0.2 times 0.2. Well, that's just 0. 0 divided by this stuff, you can't get something if you divide 0 by anything. It's still 0. So basically, we're just saying that Q equals 0. So is K greater or less than Q?
Greater, so products are favored.
So what? Products are favored, yes. So that means it's going to go that way. So the change is going to be on the product side. It's going to increase on the product side. Okay? So now we know when we have our x's here, these are all x's. Now we can tell whether or not those x's will be positive or negative. In this case, what is that? What is this x?
Positive.
Positive. And it's actually a
Isn't
positive
Two.
2x because of the 2. This, since we're increasing our products, we must be decreasing our reactants. So this is negative and this is negative. And so our equilibrium is going to be 0.200 minus x, 0.200 minus x, and 2x. Okay, there we go. Now, what do? We write that out as an equilibrium expression. We have our K, so we set 0.1 equal to 2x over 0.2 minus x times 0.2 minus x. Some more board here. So let's write it right here. 0.1 equals 2x over 0.200 minus x times 0.200 minus x. All right. Oh, and this is squared, right? Because the 2 there. Now, we can write that as 2x squared over, these are the same things. That's handy. I wonder if that was done on purpose. These are the same. So 0.200 minus x times 0.200 minus x equals 0.200 minus x squared. Oh. So now what can we do? Now we can take the square root of everything, both sides, because this is squared and this is squared. So if we take the square root of 0.1 and the square root of these things, I have to erase. Sorry, guys. Don't, you know, it's funny because, you know, when I would do this in the classroom, I had this gigantic whiteboard. I would still run out of room somehow. And now I'm squished to this little one. Someday when we get back in the classroom, maybe I'll be able to be more conservative. But anyway, so what this ends up being is the square root of 0.1 is equal to 2x over 0.200 minus x. And now you guys hopefully can solve from there. Anybody get anything? Got to distribute this, right?
I got x was equal to 0.0269.
Okay. Point 0.0269. Now, if you guys don't know, did anybody else get something different for x? Okay. If you don't know how this was obtained, come see me or Arina or Sean after lecture, okay? But essentially you take 0.2 minus x and you distribute it with the square root of 0.1, right? So you get 0.2 times 0.1 minus 0.1, square root of 0.1x. You get the x's on one side and just straight up algebra there, okay? Are we done? Nay, we are not done. Now we have x, we have to put it in the context of our equilibrium. So now this becomes 0.2 minus 0.0269. 0.0269 times 0.0269. And if you do that math, what do you get? Anybody?
I got 0.173 for the first two, and then
Okay.
0.0538 for the last.
0.053, okay. 8, did you put an 8 on the end of there? I thought I heard maybe.
Yeah, there is an 8 at the end.
Okay. Anybody get anything different? Got the same. Thanks, Rachel. Okay. I hope that you guys are all doing this, following along, writing this stuff down, even if you don't get to the answers as quickly, right? Because if you're not, if you're just sitting there trying to absorb it, then it's going to make it hard when you actually have to take pen or pencil to paper and do this stuff. So don't feel bad if I'm going through these problems a little bit quicker than what you can do to get to that final answer. We all have our different paces, and I'm just trying to get through the material so that we cover enough and that we do enough practice problems. But again, I really hope that everyone is at least writing stuff down. Okay. So let's go back. Okay. Where did my? Oh, I see. There it went. Okay. Let's share the screen again and do another problem. Okay, that's the one we just did. Now we're going to do, this one should be pretty familiar, this reaction, right? Dinitrogen tetroxide going into nitrogen dioxide. They give us the Kc. They give us initial concentration for nitrogen dioxide, and they want nothing else. Okay. So I will give you a little hint off the bat, since we don't have those nice two concentrations that are the same, that are going to end up in a square, and then we can just take the square root of both sides. It's not going to work out like that. Okay. So let's first set up the ice table. Let's do this. Set up the ice table, and then I'll give you the next little useful tool to get to the answer. Okay. All right. So hopefully you've got at least this much set up. What else do we need to do next? We need to find the direction that it's going. So we find out Q. We say Q is equal to 0.100 squared over what's this? That's 0. Now, if you put 0.100 squared divided by 0, you might get an error. Or depending on your calculator, you might get infinity. Infinity and beyond is a very large number. So when we have a whole number, something greater than 1, or greater than 0, divided by 0, we get infinity, and Q is then going to be much greater than K. So which way does the reaction proceed?
To the reactants.
Yes, Q is greater than K, so it's going to go this way. So the change is going to leave here and go there. So then how do we write that in terms of our change? What is this? Plus, right? Because it's going this direction, so it's gaining the change. It's leaving this direction, so it's a minus 2x. 2 because of the coefficient. Okay. So then what is the equilibrium representation? It's 0 plus x is x, and then 0.100 minus 2x. Take a moment to write out the equilibrium expression for it now. And then we solve for x. Set it equal to 0.36. So okay, maybe you got something like this. Now, if we write that out, what does that look like? Anybody? We get essentially 0.100 minus 2x times 0.100 minus 2x, right? That's the same way as writing this squared over x. Now what do? You distribute. Distribute this top here. So forgive me, I need to erase our top part up here. We can say that 0.36 equals 0.1 times 0.1, right? What's that? Is that 0.1? Minus 0.1, right? Then times -2.
I think that should be -2x on the second one.
Oh, sorry. Thank you. So what's that going to be? 0.2 x what else we got? What's a -2x? What's a -0.2 minus a -0.2? That's a -0.4x plus 4x squared, 0.0100. All right, my autocorrect, does that look right to you guys when you distribute that?
Yes.
Okay. Now, here's the hint. We can't solve that just like that. But, whoops. Good old quadratic equation will save us. You guys remember the quadratic equation?
E equals -b plus or minus square root over
So,
2.
what do we got? We've got our a right here, 4x squared. We got our b right here, the 0.400x. And we got our c, the thing without a variable. So now all we have to do is plug that in to solve for x. So x equals a negative 0.4. Well, actually, let's write this out in the quadratic equation order. Okay. So what would that look like if we for this top line here? How would we write that out? Anybody?
4x squared minus 0.76x plus 0.01 equals 0.
Did you already get rid of the x in the bottom?
The x in the bottom. What do you mean? I'm not quite sure.
The x we were dividing by x down at the bottom. I'm just trying to look through it. I may have just step.
You multiply it to the 0.36, and that's how you deal with that.
Right. So this would all be, sorry, I did skip. Yeah, you'd come over here, x like that. And then you would subtract 0.36x from this to get 0.76 x. And then now this becomes 0. You guys follow that? Yeah. So this x down here, it's multiplied to each side to get 0.36x. Subtract it here. Negative 0.4 minus 0.36 is 0.76x. And then what was the last one? Plus 0.100. Okay. So now that we have this equation, how do we pop that in? Erase this. To this. Now we have x equals a negative, remember this is A, B, C, a negative 0.76 plus or minus the square root of b squared. So 0.76 squared minus 4a, which is 4, c, which is 0.1, all over 2 times 4. Whew. Okay. And now we're going to get two answers. We're going to get one answer where we take this and add it to this over this. And then we're going to get an answer where we take this and we subtract it from this and then take that over 2 times 4. Let's see what you guys come up with. And I'll do the same. Oh. Sorry guys, that needs to be negative. This is a negative 0.76. Oh. Sorry guys, I think I have another error too. Drats. So 0.1 times 0.1 should be 0.01. Bad math. Sorry about that. Now let's see. Okay. So I got one value being x equals 0.176 when I add these together. Now I'm going to do the other one. So I'm going to take negative 0.76 squared minus 4 times 0.01. I'm going to take the square root of that. Square. Shoot, typed it in wrong. Did anybody get the next one?
I'm failing to type it in my calculator. I keep getting domain error.
Okay. So it's all about the process. Okay. So one thing you can do is you can just solve for the numerator right here under the square root. That's what I'm going to do. So I'm going to take a negative 0.76 and I'm going to square it. And then I'm going to subtract that by 4 times 0.01. And I'm going to take the square root of that. And that gives me 0.65. Okay. So we can say that all of this stuff is 0.65. If that's 0.65, then a negative 0.76 or a positive 0.76 plus 0.65 divided by 2 times 4 or 8 is 0.176. or 0.76 minus 0.65 divided by 8 is, so it's this or 0.014. Did anybody else get something like that? Okay. Great. Great. Thank you. So now which one is it? Well, in order to find that out, we plug it in to our equilibrium. Okay. So let's plug it into this one over here. Let's say 0.1 minus 2 times 0.176 equals, I got a negative 0.252. Now that should be a red flag because you can't have a negative concentration. So let's try the other one. We're gonna try this one now, 0.014. So 0.1 minus 2 times 0.014 equals 0.072. That seems more appropriate. Okay. So we're going to stick with this as X. And now we know what the final concentrations are. At equilibrium, it's 0.014 and 0.072. Whew, man. Is it just me or is it getting hot in here? I guess it is just me because I'm by myself, but maybe it's getting hot on your end too. I think we need to listen to Ice Ice Baby to cool off. So that's it for today. Unfortunately, ran out of time to do any more problems. But this is as hard as it gets, okay? Using the quadratic equation to solve for X. Currently shivering in my room. Okay, I'm sorry. So some of you guys are cold. So maybe you need to warm up a little bit. Do some jumping jacks or something. That might help. Otherwise, I know that this is, might be challenging. Maybe it's not. Maybe it's easy. Try to do this again. Then watch the video and see if you get the same answers. Okay. I think I would like to do some more ICA problems. And maybe what I'll do is I'll record a video of doing some more of these, or we could try to do some during office hours or something like that, because I really want to give you some more examples of these. Unfortunately, they take a lot of time and I don't want to keep you guys past your schedule for this class. But if you guys are stressing out about this, we'll get through this. If you aren't stressing out about it, good. Enjoy your weekend, get your abstract to Arena. And I'm going to try to do a virtual on-campus lab again next week, hopefully with some acid-based stuff. But if not, then we can use some time during lab to do some more ice tables, okay? More problems. Because again, the more you practice this, the easier it becomes. All right, any questions before we wrap up?
You said after class, if we didn't understand how to get X in that one equation to stay afterwards.
Did I? Which question?
It was the one with nitrogen plus oxygen going to 2NO, and like you squared the entire side of both sides to somehow get X.
Yes.
But I got like most of the way there, but then didn't know what to do. So it was that problem that I didn't know how
Okay.
to do.
Well, really all you have to do, everyone else, you're free to go if you want to, or you can stick on if you want to. Either way is fine. Because we had a situation where it was x squared over x squared, we can get rid of that square by taking the square root of it. Okay. So I want to say it was like 0.1.
I have everything written down, so it's this is where it got uncertain. After we have the square root of 0.1 equals 2x over 0.2 minus x, I thought multiply by the 0.2 minus x on both sides,
Yes.
and then you get that equaling 2x, and then distribute the square root of 0.1
Minus x equals 2x.
Okay, and I did the 0.2 times the square root of 0.1 and got like an answer. Should I just leave it as that for now though?
You took 0.2 times the square root of
Yeah, and then I ended up with 0.0632. But should I just leave it as the square root of 0.1 for now?
Oh, no, that's fine. So when you take 0.2 times the square root of 0.1, what did you get again?
0.0632.
0.632 minus what's the square root of 0.1?
That I didn't find out. I can do that.
Okay.
0.316.
0.316x equals 2x.
So that's as far as I got. Then I wasn't sure what to do to isolate x.
Okay. Gum, do you have any ideas of how to isolate x?
I can't see it. Let me see.
Oh, sorry. I'll get out of the way. All right, I don't mean to put you on the spot, just trying to see if maybe someone else explaining it is a little bit easier.
There's a question mark in the comments, so at least someone's as confused as I am, and I'm not alone.
Absolutely.
These let's see, 0 point.
Would you add the yeah, Chase, do you want to explain it?
Since 0.316x and 2x have the same degree of x, whereas x isn't to a power, or it's to the 1 power, you can combine them together. So that way you have x together.
Exactly. Exactly. Sorry. It's just getting to that time where I just get kind of, I don't like, I end up getting a little silly. Exactly. Right, Chase. So it has the same variable. So you can now add those together. So we get 0.0632 equals 2.316x. Divide each side by 2.316. 0.316. I don't know if hopefully I don't know if you can see this. Getting kind of low. Boop. 2 is not showing very well. And what do you get for that?
Sorry, I'm still writing it down.
That's okay. Sorry, I'm just now checking the chats. Thank you guys. I see that now you're.
Okay, yeah, I got almost the same thing. I got 0.0273, whereas in lecture we said it was 0.0269.
Okay.
I got that too. Yeah.
Okay.
So we got the right answer just now or in lecture?
Yep.
Right now.
That's pretty close. It's gonna, so 0.0269 is 0.027, right? If you round it. So something's off a little bit, and I don't know where that happened. It might be the square, it might be the sig figs that people did for the square root.
Okay, thank you. And I think it was just that I was brain dead at the point where you needed to add the x's together, because I got addition mixed up with multiplication, and then I was like, well, then you have x squared again. But when you add the x's, it doesn't make it x squared. It's just adding like terms.
It's not multiplying. It's
Yeah.
adding. So and I think I brushed over that part. I don't think I went through all these different steps to try and get time to get to the other one. So totally.
Yeah, no, you didn't. You just went as far as the square root of 0.1 equals 2x over 0.2 minus x. And then you were like, if you don't know how to get to x, then come see me or Erna.
Okay.
So that's what I'm
Well,
doing now.
Now
thank you.
it's all good. Now you don't have to. And I'm still recording, so I think, yeah. So anyone who watches this recording will have that added benefit of going over this. So thank you, Hannah, for asking that question and asking to go through this completely. I don't usually like to skip steps, like every single step, but sometimes for the interest of time, I do. Okay.
If it's really simple algebra, then it makes sense to skip them.
Yeah.
I was just
It is simple.
not the greatest at algebra, and so sometimes I get a little mixed up.
Yep.
And
That's totally normal.
going through it is what I have to do to make it make sense.
Perfect. Yeah. Math doesn't come to everyone the same way. And so it's perfectly normal to get mixed up, so don't fret, keep asking questions, keep going over these problems. I recommend, again, doing this again, see if you get the same answer. Not only does that help you go through the progression, but it also helps you practice typing it into your calculator. A lot of students get wrong answers simply because their order of operations are wrong, or they type in the wrong number or the wrong sign. And so the more you practice and get familiar with your calculator, also, the higher likelihood of success you'll have with your calculations in general.
Yeah, and I noticed on my calculator, it's really picky about putting in parentheses. And So I was kind of wanting to figure out how to do it on the iPhone because it seems faster, and the iPhone is what I'm gonna have with me most of the time. But yeah, when I was in Chem 101 with Sean, he was just like, when in doubt, just add parentheses.
Yeah. And I would say that anything in this class that we're going to be doing can be done on an iPhone calculator or even your simple calculator app if you have one of those. Um, it should be plenty sufficient for doing these kinds of calculations.
Yeah. And chemistry was really exciting for me in high school because all of these abstract algebra concepts were finally making sense when for so long I was like, it just doesn't make sense. Why are we doing this? So that was really exciting, and that's what made me really love chemistry. So I'm grateful for the mathematicians that give us chemists the equations that we need to figure stuff out.
I mean, you know,
With
people. Oh, sorry, was that gum?
oh, I was just gonna say, without mathematics, chemistry would not exist. So
I mean, you know, mathematics, again, like I said, I think at the beginning of this quarter, mathematics is the language that we use to understand how matter interacts with other matter and changes. And yeah, so many people say, well, why did I have to learn algebra? I haven't used it since. Well, if you're in chemistry, you will. And chemistry is the study of matter interacting with matter. And so by even if you're not doing chemistry, it relates to you in some way, right? So great. Okay.
Dr. Franz, I was just gonna ask, since we have our rough drafts due for the abstraction,
Mhm.
I have 8 reference for the project, and I don't think I will be using all of them necessary for the abstraction because it will just go over more than a page. So, what would you recommend? Like, is it only going to be 1 page, or can we go more than 1 page for the abstraction? Because
You can
I'm
go,
gonna be. Oh, sorry. Go ahead.
sorry, yeah, you can go a little bit over a page if you want. It's better to go a little bit over than go a little bit under.
Okay.
Okay.
Cool.
And sometimes you can also summarize a couple references in one sentence, if that's possible. Like for instance, with the journal club paper today, it was talking about the applications of liquid glass, and it said that it could be attributed to metals and biology, and then it had citations 1 through 3. So if there's any way that you can kind of combine a few references, that's a little bit of a trick to shorten up your abstract so that you're talking about 2 things, only using 1 sentence rather than 2 separate sentences. So if that lends itself to you, then that works as well. But yeah, you can go over a little bit.
Okay. Because I was gonna explain the structure and the function of Rubisco, and that literally takes the whole page, 1 page. Um, and most of the stuff, like we talked about earlier of the lecture, that if you're using like some of the information that they're presenting is common knowledge, if you're like exposed to like biology courses beforehand. But so and the nuance of what the like a proposal, I would not include that in this abstraction, right? Because it will not fit into this project, correct?
Yeah. I mean, I think for your abstract, you'll have to do your best. That's the challenge. Sometimes it's not finding what to write, it's finding what not to write.
Right, yeah.
To be succinct and still communicate the point across, right? So if you can't explain the mechanism of Rubisco in a paragraph, then you need to just try your best to condense it. And, that is the challenge for a lot of papers that scientists write, is to not write some kind of anthology or on your topic. So just do your
I
best.
was having the same problem trying to stick to a page. So
Mhm.
I get you. And also another thing was my writing tutor in middle school like drilled it into me that you have to put your perspective into the paper, so use adjectives to put in your perspective, where in this you don't really want to do that. You just want to say what it is, no opinion. It's just like
Don't get colorful.
the first sentence I wrote was like nuclear chemistry has helped us power rovers on Mars and treat cancer with radiology. Now my writing tutor would be like, you need to like put your perspective on that. So you could say like nuclear chemistry has helped us achieve these amazing feats such as this and this, and it's putting your perspective on it. And had to like turn that part of my brain off and be like, no, don't do that.
I don't know. I don't know if you could see, but I have like pages of pages written down of like the function and mechanism of the Rubisco enzyme, and what possibilities of a new upgraded Rubisco enzyme would do to the environment, and like the large scale impact. So I think I might save that to Chem 103 in terms of giving the proposal, and like we talked about early on, beginning of the semester, a quarter. So I'm just gonna stick to the guideline of our research project for this course. So I might actually continue on with this particular topic for my Chem 103 class too, because it's so rich and in depth that I could just go on it. Yeah.
Great. Perfect. And then you already have a lot of the work out of the way for next quarter.
Yeah, pretty much.
That's the goal. Yes, Hannah, you definitely don't, when you're writing, in a science publication or any kind of science document, you want to filter out any type of subjectivity. And that makes
Don't use adjectives.
yeah, that makes for some dry reading at times, right? These science papers, for most people, I've said it before, aren't pleasurable. It's not like you sit back and kick up your feet and enjoy a nice primary paper, right? But that has to be the way, because you don't want to steer the narrative. You don't, and it still happens, right? You gotta steer the audience toward your conclusion, right? But you can't. You got to be very careful doing that, because you don't want to incorporate bias into your writing. And that's very different from how other writing, creative writing works. And it takes a little bit of practice, but yeah, don't try not to use too many adjectives, as you said, Hannah, and try not to overinterpret things, right? So if you look at the figures that we discussed in the papers, they tell you what you're looking at. Sometimes the figure legend will give you the conclusions, but it shouldn't. That is a mistake. A good scientific legend for a figure is only going to describe what you see in that graphic. And it should let you make the interpretation. If it doesn't, if it says, as you can see in this figure, this is doing this, that's a mistake, because that's being subjective to a certain degree. And it's got to be, now they can, like I said in Journal Club this morning, they can get a little bit more subjective in the discussion section, right? When they do their conclusions, they can kind of say, we think that this is going on. And this might be really awesome because we can use it to do something really cool. But when they're presenting the data, the correct way to do it is to just describe what you are seeing, and that's it. And so with this project that you guys are doing, it's the same thing. You are introducing your topic to an audience. The audience is your classmates, and you want to do it objectively. Now, of course, it's for the purposes of this class, it's okay when you're presenting your poster to get a little jazzed about it and get excited and say, hey, I really think nuclear chemistry is cool. That I'm not going to penalize you by any means, because we as a group want to get excited about your project, right? Or if you want to say Rubisco is really cool. Or Chase, if you want to say, I really like the idea of repurposing drugs because it saves a lot of time and it can really speed up the pipeline. Like, that's perfectly fine. It's when in our writing we do that then it has a way of swaying the reader, and you don't want to sway the reader. And ideally, when we read these papers, we become more critical of the papers and we say, I think that they're trying to sway me there. So anyway, sorry, long-winded speech on that, but good points, guys.
Just one quick question, Dr. France, is that my trouble is with this abstract is that finding the information that I'm exposed to in terms of the reference that I've already read, is that like what is common knowledge and what points I should be referring in terms of like the giving credit citation.
Well, a lot of the Rubisco mechanism is going to be considered technically common knowledge because the mechanism's been just, biochemically
Kelvin cycle,
a long time. So if you spend most of your time just describing the mechanism, then what I would do is I would just, combine your sentences into one, combine two sentences into one, and then cite it from the source that you got that from.
Okay, cool.
Okay.
Thank you.
And really, like, what you eventually want to do is start talking about using Rubisco for synthetic biology, right? If I remember right. So then that's going to get much more into your citations, because
that's not common.
Yeah.
We're still recording, by the way.
Yeah, I know. I figured that's, I mean, assuming you guys are okay with it recording, I figure if someone wants to watch this, they may get added benefit for their abstract as well.
I had a question.
Are you guys, wait,
about
before you ask that question, are you guys okay with this being recorded?
Sure, definitely.
Because if not, I can trim this all. I can trim this all off the recording if you guys don't want to. But if you're okay with it, I think this is a good learning experience for students who didn't stick around.
Yeah.
Okay.
I just thought maybe you would want to stop it since it wasn't relevant to the lecture. But I'm okay with it. For the citations on the instructions for the research project, it gives examples, but you never state what the format's called.
I don't care. MLA, whatever you want to do, it doesn't matter as long as it's consistent.
I was going to use MLA, just saying.
I think when I just typed in one of your citations and like said like what format is this citation, it said it was an APA.
Yeah, APA. Whatever you want to do, Hannah. If you want to take just, if you wanted to just say, okay, here's a paper I'm referencing. How did they reference the papers, their papers that they use, their citations? I'm going to use that format. Fine. Just make sure it's consistent, right? I don't want to see inconsistencies from one reference to the next. That might get you dinged, but it doesn't matter the format. This is not an English class, so.
Yes, and I like that because I would lose points off of not having a period in the right place for a citation. It was incredibly frustrating, and so the citations are usually the most stressful part.
It's important, right? If you submit a manuscript for publication, a scientific manuscript, and you've got typos and you've got different formats and you don't have each journal has a specific format. right? If you look at these papers and you look at PNAS and you look at PLOS and you look at Nature and you look at Science and you look at Cell, they all have different formats. And if you submit it and you don't abide by those formats, you're going to get that paper tossed right away. So I don't mean to de-emphasize the importance of dotting your I's and crossing your T's and putting in periods and submitting to a certain format. That is important. It's not important for the purpose of this project. My emphasis is for you guys to research something and then report on it. So it's important, but just not as important to me as other things.
Also, there was some stuff that I left out of my abstract and outline for like the rough draft that I wanted to figure out more about and possibly put it in there. But maybe not. It's kind of, to me, more like the history of science than the mechanisms. But like I kind of wanted to mention Marie Curie, because she like did a lot of research on radioactivity and discovered radium and polonium, which was pretty important.
She also coined the term radioactive.
Yeah, like
Didn't she?
there's a bunch of stuff that she did, and I left that out of my outline and abstract because I didn't have a whole lot of good sources at the time.
Okay.
So I want to go back and possibly put that in there. However, it is more history than it is.
Put it in your final draft.
All right.
It's okay.
I wanted your advice on that.
Oh, well, wait a minute. This was in your final draft, but it's not in your rough draft. So no, the rough draft is just to get you guys, again, plodding along and keeping you guys, on topic and on time. So add it to the final draft. That's perfectly fine. And today, this month is Women's History Month, right? So what better time than now to add in a little bit of history on a really, really groundbreaking female scientist, right? She also won 2 Nobel Prizes in 2
physics
different
and
categories.
chemistry.
Yeah, right.
Yeah.
So, and unfortunately, she succumbed to studying radioactivity. But yeah, go for it.
All right, cool. I would just wanted your advice on that, whether to put it in or leave it out, because it is history more than it is science.
Yeah, and when you do your, and if you your poster you can add stuff into that, right? When you make that slide in PowerPoint, put a picture of Marie Curie on there and talk about her and say, I like science. I really am interested in nuclear chemistry, and I'm a big fan of Marie Curie. Or I don't know however you want to, do it, but like that gives a personal touch, and that, as I said, is okay. Not necessarily in your abstract, but in your presentation, it's good to say why you're interested in the topic that you looked at, right? It's okay to put a personal touch on that, because then you draw in the audience. They say, oh, this is meaningful to them. And maybe if that meaning is infectious, maybe I'll find meaning in it too. But if you just go up there and spit off some topic that you're half-heartedly interested in, well, why should I get excited about it? If you're not excited about it, there's no reason why I should. So by all means, when it comes to the presentation, please feel free to add in the value of that project to you personally, if you can.
Dr. France, I'm pretty sure you're going to go over how this presentation is going to be set up and scheduled. But I was just wondering, is it going to be towards the last 2 weeks of our quarter we're going to do the presentation, or is it going to be all last week?
So I have presentations scheduled for week 11.
Okay.
So 2 weeks from now.
All right. Cool.
Hopefully, my plan is that we can use those. I might have to use 2 labs. I have an ICA scheduled for week 11, but we'll just see, how many presentations we get done on Tuesday And if we need to do some on Thursday, we'll do that as well.
And how much time would you give for each individual? Like 5 minutes-ish, or is it?
5 to 10 minutes.
Oh, okay, cool. I don't know if I should send you this privately, but I was just gonna ask you anyway. I turned in the wrong assignment for ICA 6 because I thought week 8 I have to turn in the outline. So I turned in the outline to ICA 6 rather than the outline, because at the time you didn't have the outline assignment posted in Canvas. So I just posted the outline in ICA 6 rather than doing the instruction how to find another resource. So and I cannot resubmit and go overdo the ICA 6 because it's only allowed one time.
Oh, okay.
On my side, I don't know if it's for everybody else, but
Okay.
yeah.
That is kind of odd. I remember once I like submitted a portion of the ICA, like I finished the first question and submitted that, and then through submitting again, I could still submit like the rest of the work.
Hey, Gum, would you send me an email?
Email, I would do that. Yes, for sure.
Just to remind me. I'll look into that and we'll see what we can do.
Thank you.
All
Really
right.
appreciate it. Have a good
right.
day, guys.
Nice
Thank you,
chatting.
Dr. France.
Have a great
Bye.
weekend. We'll see you Tuesday.
And I did receive the email with the doodle poll. I'll be posting that on the LTCC app today.
Great.
Thank you, Miss President. Yep. Hannah.
Real quick, I have a quick question about the outline, and then I also have a question on the notes and also the draft in general. I didn't want to interrupt anybody.
Okay. Is it okay
for
still recording? Is it okay if we're still recording? You want me to stop recording now?
I'm totally okay with it recording, just in case like this answers anybody else's questions.
Great.
So for the rough draft, or not for the rough draft, for the outline, did you want us to include our 5 sources on the outline? Because I was going through the instructions for it and it said you wanted it, but I didn't read that until like last night.
No, that's fine. I think you sent me maybe you sent me a message about this.
Yeah, I did.
No, that's okay. Again, that's to kind of just I wanted to make sure that people were having their sources ahead of time. But that's okay if it doesn't have the references. That's not a big issue.
Okay. And then for the not for the outline, for the draft now, you want us to email it to Irina by tomorrow, right?
Yes.
Okay. And then I'm also just having like a little trouble just writing the draft. I've gotten about halfway through it, and I guess I feel like I can like get a full page, but I don't know like how confident I feel about the information I'm putting down.
Okay.
And it's just I just kind of like I'm just kind of like not entirely sure about what I'm putting onto it, I guess.
Okay. Well, first of all, submitting something is better than submitting nothing, and submitting partially something is better than submitting nothing. And really, the people like if you give it to Erina, I'm not going to give you a bad grade because she put a bunch of comments on it. I'm going to give you a bad grade if you didn't submit anything to her. Okay. So get her what you can. The whole point of this is to get someone else looking at your document rather than just you, because maybe she'll have some pointers for you. Maybe she'll say, maybe you could explain this a little bit better, Chase, or maybe, I don't know. It's always good to get different eyes on your writing. And so does that mean you just throw a bunch of nonsense on there to fill the page? No, you don't want to do that. But just do your best to write what you feel confident in. And if it's not quite a full page, that's okay. It's a draft. It's a rough draft. And then you got all next week to work on the final draft. So that would be my advice on that. Okay. And remember, if you start with your topic, and then get into why it's important. And then you start going into the examples that we talked about, like to pick 2 or 3 examples of successful drug repurposing. And it's double spaced. I think that you'll find that the page will fill itself better. Okay.
Okay. Yeah, I've gotten about like halfway introducing it, and then also like why it's important so far. And then when I got to like the examples and stuff, I think that's where like I kind of got bogged down and like a little confused.
Okay. Then, like with these journal club papers, one trick is to extract the just most salient points, right? So when I went over the journal club today, we didn't cover every single figure, every single panel in each figure. I tried to highlight what I thought was the most relevant stuff to the overall topic. So try to do that yourself. And that's hard. I'm not saying that's easy. It can be challenging to say, okay, what's the take home message, right? But look at so if it's a paper, for instance, look at the abstract, look at the conclusion. Maybe if it, depending on the paper, like today's paper, they had a significance box, right, in the paper where they kind of just said why it was important. So try to look for those things and use that as a guide to condense it into just the most relevant parts.
Okay. And then one last question I had was for the notes when we were doing the ice tables. For the last example, when we used K and Q, I got confused on why we were using K and Q, or like how it worked overall, I guess.
So K and Q, their relationship to each other will tell us which direction the reaction is going.
Okay.
So for our ice table, we got X, X, and X. And we want to know where the change is happening. We want to know which X's are positive and which X's are negative. So to do that, so in the very first ice table, they gave us one of the equilibrium concentrations and they gave us one of the initial concentrations. And by subtracting those or adding those, looking at those relationships, we could determine the change. But if we don't have an equilibrium concentration, we only have, an initial concentration. Then we don't know which way the reaction's going to predominate. The way to do that is to compare K and Q. And in those problems, they give us the K, right? We need the K to solve for X, because if we don't have the K and we don't have the change, then we have 2 different variables and we can't solve it. So they give us a K, and then based on that, we do our reaction quotient, our equilibrium expression with the initial concentrations. That gives us Q.
Okay.
K, whatever the value is for K, that is going to be equal to the concentrations at equilibrium. If you wrote out these, let's say you do all this and you get something for this and this and this, and you write that out as an equilibrium expression, then it's going to be equal to K.
Okay.
Initially though, that's not K, but we can say that that's Q.
Okay.
When Q and K are equal to each other, it's at equilibrium. When Q and K are not equal to each other, then it's going to go in one direction or another, depending on how they're related. So if K is greater than Q, it's going to predominate this direction toward the products. However, if K is less than Q, it's going to go toward the reactants. So that is why in those ICE tables, we needed to solve for Q. And in the first one, Q was 0, so it was smaller than K. And so it went toward the reactants. And so if it's going toward the reactants, now we know that the the products. K is greater than Q, it goes toward the products. And now we know that the change is happening in favor of the products. And so this is positive, and this is negative, and this is negative. When Q is greater, when K is greater than Q.
Okay.
But second problem, it was infinity. And so we said that's a lot larger than K. So if Q is larger than K, then it must be going toward the reactant side. Because by definition, when Q is greater than K, it shifts toward the reactants.
Okay.
And if that's the case, now it's reactant favored. So the change is in favor of the reactants. And so they're going to get a net accumulation of change, and they'll be positive and products will be negative.
Okay. That clears it up a lot.
Okay. Sometimes hearing it a second time around or a third time around makes it much more easy to understand. Sometimes maybe I take liberties and I miss explaining something quite succinctly as that. So always feel free to ask questions and follow up on things that don't quite gel, because oftentimes I can explain it better, and getting it a second time around makes all the difference. So
One more quick question. How would we find Q in this little example?
the initial concentrations.
Oh, okay.
So we would say, if this is 0, remember Q is the reaction quotient. It's concentration of products over concentration of reactants. K is also that ratio, products concentration over reactants, only it's when those concentrations are such that the reaction is at equilibrium. So to find Q, you would just take the concentration of 0 over the concentration of 0.5, in this case, times the concentration of 0.2.
Okay.
0 divided by something is 0. So then we would say we'd say Q is 0. And then I would give you the value for K, and that would be greater than 0. And so that would be favoring the products, and so X is plus and the reactants are minus.
Okay. Okay, that makes a lot more sense now.
Great. And then, like I said, K is going to be the concentrations of your equilibrium. So when you solve for X, you'll take 0.5 plus whatever that value for X is, and that will give you the concentration at equilibrium. You'll take 0.2 plus X. Well, in this case, we said that Q is less than K, so it's product favored. So really, in this case, it would be plus, minus, minus. And so our concentration at equilibrium would be 0.5 minus whatever the value for X is once we solve it, 0.2 minus the value of X, and then 0 plus X.
Okay.
And then if you took it a step further and you took whatever those concentrations were and you wrote them out as an equilibrium expression, it should equal your K that you were given at the beginning. So that's a good way to check and cross-reference and make sure that you did it right.
Okay. Thank you so much, Carl.
You're welcome. Have a great weekend.
You as well.
I will.
Bye-bye.
See you next week.